Hello, in this video, we will be measuring the convection heat transfer coefficient of the air in my apartment by analyzing heat transfer in this aluminum sheet. The system is experiencing transient conduction as the temperature is changing with time. There are three methods that can be used to model heat transfer in the aluminum sheet. The lump capacitance method, which is valid when the BL number is less than 0.1. The semi-infinite solid method, which is valid when the Froude number is less than 0.2. And the specific geometry method, which is valid when the Froude number is greater than 0.2 and the specimen is a plane wall, sphere, or infinite cylinder. Because the aluminum sheet is not any of these geometries, we cannot use the specific geometry method. The thermal conductivity of aluminum is 237 watts per meter Kelvin. The surface area exposed to the environment is 0.0124 square meters, and the volume is 4.7 times 10 to the negative 7 meters cubed. This means the characteristic length is 3.4 times 10 to the negative 5 meters. To solve for the maximum convective coefficient that would make the lump capacitance method invalid, all the parameters were plugged in, including the max BO number of 0.1, and the equation was solved for H. This tells us that if H is above 697,000 watts per meter squared Kelvin, the lump capacitance method is not valid. The convection coefficient for air is between 5 to 30 watts per meter squared Kelvin, so the lump capacitance method is more than valid and will be used. The assumptions made in the experiment include that the thermal conductivity is constant throughout, that there are no temperature gradients inside the aluminum sheet, that the sheet is purely aluminum, that H is constant, and that the sheet is a perfect rectangular prism. In the experiment, a pan was put on the stovetop, turned up to the highest setting, and allowed to equilibrate. The aluminum sheet was then put under the pan. It was done this way so the top side was not exposed to the environment. After a few minutes, the aluminum was removed from the heat source and the temperature was measured with a temperature probe. A timer was started before the data collection so that no time was wasted trying to start the timer during the experiment. T infinity was collected beforehand. The temperature initially goes up as it comes into contact with the sheet. This is the temperature probe catching up to the actual temperature of the sheet. This will be talked about later. The aluminum sheet and temperature probe were not in the frame as it was easier to do it that way. The temperature data was transformed into the form T minus T infinity over Ti minus T infinity so that it fits into the lump capacitance equation. T infinity is 24 Celsius and Ti is 53 Celsius. Additionally, a timer was started a few seconds before the experiment, so the time data was transformed so that the experiment started at T equals 0. A clear exponential decay is seen, which is expected. Then, the natural log of each side of the equation was taken. We should see a straight line when plotting the natural log of the temperature side of the equation versus time. The slope of this line is equal to negative HAS over rho VC. When plugging everything in, we get a convection heat transfer coefficient of 2.1825 watts per meter squared Kelvin, which is a bit lower than expected. When looking at the metal sheet, it's clear that it isn't smooth. It has some ridges and etches in the surface, which increase its surface area. An increased surface area decreases the convection coefficient, and this was not taken into account. Additionally, during the experiment, heat is being transferred away from the sheet via conduction from the metal probe and the metal forceps, so the change in temperature is greater, so the apparent convection transfer is higher than what it actually is. However, the surface area over which this occurs is very small because the area where these two metal objects are touching the sheet is small. Therefore, the effect on the convection coefficient is negligible. The biggest contributor to error is the probe itself. When measuring the temperature of boiling water, it was 4 degrees below where it should be. Additionally, the temperature displayed by the probe seemed to be lagging behind the actual temperature. At the beginning of the experiment, when the probe was put into contact with the sheet, the temperature went up instead of down because it was catching up with the actual temperature. As seen from the graph, the data should have been in a straight line, but towards the end and a little in the beginning, there are periods where the temperature stays the same for a long period of time, indicating how the probe lags behind. This definitely affected the slope predicted by the model, which in turn affects the calculated convection heat transfer coefficient. Thank you for watching my video and have a great day.